Good afternoon, teachers and students. Thank you so much for joining us. We're going to get started here in about another 3 minutes, so please stay tuned. Thank you so much.
Hello, everyone. I'm Congresswoman Deb Holland, and I'm honored to share a few words during this year's Discovery Festival. The 6th Annual Discovery Festival, hosted by Big Brothers Big Sisters, has become a wonderful tradition, providing a wide array of opportunities for New Mexico students to discover the future of STEM. New Mexico is home to many historic and consequential scientific breakthroughs, discoveries that range from revolutionizing the way we'll power the cities of the future to expanding our ability to explore the cosmos. This year, for the first time, Big Brothers Big Sisters of Central New Mexico is hosting Discovery Fest virtually. I'm amazed at how many events and presentations this team has put together under such challenges this year, and I'm delighted to see that a record number of New Mexico students will join the fun and the learning of Discovery Fest. New Mexico is an amazing home for technology, and our kids are in a great position to learn more and take advantage of our state's unique and important role in the national tech space. In Congress, I support expanding STEM. Opportunities like Discovery Fest and fighting for resources for your incredible teachers, because I know how important science, technology, engineering, and math will be for our future. I want to let you all know about my annual Congressional App Challenge that invites students to come up with one-of-a-kind apps and have their app displayed at the national level. Students learn to code, manage a project, and learn more about technology. In that spirit, I'm thrilled to welcome this future generation of innovators, inventors, and explorers, and all the incredible teachers developing these bright young minds to this year's event. Our beautiful state of New Mexico, America, and frankly, our whole world's future will be counting on the creativity and innovative spirit of you young people. So I want to encourage all the future physicists, researchers, biologists, and engineers watching right now to keep reaching for the stars. Learn all you can, and most of all, have fun at this year's Discovery Fest. Thank you.
Great. Thank you so much, Congresswoman Holland, and welcome to everyone who's joining us on this live stream from all across the state of New Mexico. We are so happy you're here. My name is Will Toppy, and I'm the Advancement Coordinator for Big Brothers Big Sisters of Central New Mexico, who puts on this amazing Discovery Festival every single year. So I'm going to just real quick talk about what Discovery Festival looks like normally, and then what Discovery Festival looks like this year inside of the pandemic. So normally Discovery Festival is a one-day event held at the Albuquerque Convention Center. We get about 3,000 students from all across Central New Mexico to engage with 50 plus exhibitors from across various areas of STEAM. And of course, STEAM, as we all know, stands for science, technology, engineering, art, and mathematics. It's a super fun event that our kids and our exhibitors get a lot out of. Now, of course, this year, due to the novel COVID-19 pandemic that we all find ourselves under right now, unfortunately, we've moved our entire Discovery Festival totally online and are hosting a series of live streamed webinars throughout the month of November. This is awesome because students and teachers can ask questions live to the presenters. So this is not a pre-recorded video. We're all here live, and you'll see all of our exhibitors here in a little bit. So just stay tuned. And I see some awesome things. So I'm going to lay some quick ground rules about our YouTube stream. So first of which, if the stream goes down for whatever reason, so I don't think it will, but hey, this is technology, and we all know how technology can be sometimes. So if the stream goes down for whatever reason at all, go right back here to the BBBS CNM YouTube page, and we'll have the stream back up shortly. I don't think anything's going to happen, but you never know in this day and age, right? Secondly, this is great. I see we have a chat function, and so you can post in there, post inside the chat where you're watching from, what school you're watching from, and any questions you have at any point throughout this presentation. Okay, the chat is really active right now. This is so awesome to see all your comments. I'm gonna be sharing them and reading them live on air. So please, again, any questions at all at any point, type it inside that chat. Teachers, if you're airing this live stream inside of your Google Classroom, please, if your kids have any questions inside that Google Classroom, pass it on to our YouTube chat. Let us know the name of the student who's asking it, and we'll shout them out on the program. I want to give some shout outs here as we get started. Looks like we have Lowell, 3rd grade, 4th grade, and 5th grade who are all watching. Thanks so much for being here. We have Bill Seifert from Cibola High School. Welcome, Cibola. That's awesome. We are so happy to have our high schoolers here. Let's see here. We have Roxanne Morris from APS Title I who's watching now. We have North Star Elementary who's joining us. We have Osuna Elementary who's in the house. Woot, woot. Welcome, Osuna Elementary. We have, let's see here, Miss Williams's class who's also watching here. Let's see. Getting a lot of, it's a great chat. It's hard to keep up with it, but welcome everyone again. Thank you so much. We have Eva B. Stokely Elementary who's joining us. We're so happy that you're here. Now, as we get started, I also want to quickly, as we begin, give a couple of shout outs to some amazing sponsors. The program that you're seeing now would not be possible without the support of these sponsors and these folks. So big thank you to our Da Vinci presenting sponsor, Honeywell. Honeywell was on earlier today. If you missed out on their presentation, don't worry. You can go to our website, discoveryfestnm.org. We have all these videos end up as recordings on that website. So if you missed something, if you missed a presentation you wanted to check out, go to that website and you can view all of them. So thank you so much, Honeywell, for your partnership this year and for always. Honeywell is a great sponsor and advocate of ours. To our Curie sponsor, Fidelity Investments. Thank you so much, Fidelity. They normally have a three booth long exhibit at Discovery Festival that the kids get a big kick out of. They spoke about this year, what is credit and what is savings, and how to save. So please take a look at those videos on that website I mentioned earlier. To our ride sponsors, Aztec Machine and Repair, based out of beautiful Bloomfield, New Mexico, and to Air Force Research Laboratories, who's coming on here any minute. So just stay tuned. They're going to be talking about satellites. You guys are going to absolutely love this program. So thank you to both Aztec and AFRL, Air Force Research Laboratories, for your partnership this year. And finally, to our Newton sponsors, the Defense Threat Reduction Agency, DTRA, as we like to call them. They're coming on Thursday. So if you're watching from a middle school, I'll shout out to all of our middle schoolers who are watching. If you're in middle school, come check out the Defense Threat Reduction Agency's presentation on Thursday. They're doing live polling, analysis, scientific discovery, all in the live stream. Please come back for that. You're going to get a big kick out of it. To Kirtland Air Force Base, thank you so much. To Micronet Solutions, Sandia National Laboratories, and all of our heroes at Presbyterian Hospitals, thank you all so much for your sponsorship. I'm going to give a few more shout outs we had come in here. We have some more students from Cibola High School. Thank you so much for being on. We have the gifted math from Desert Ridge Middle School. Awesome. That's so great. Welcome, Desert Ridge. We've got more students from Desert Ridge. We have Roosevelt Middle School. Welcome to the stream, Roosevelt. Let's see here. Awesome. Okay, we're getting some great comments and everything like that. So keep in mind, please post your questions throughout this presentation. Without further ado, wow, I am long-winded and I'm sorry as always, but I'd like to introduce Matt Fetro, who is a scientist with AFRL. Matt, do we have you on the line?
I'm here, Will. Can you hear me okay?
Awesome. We got you loud and clear.
Hey.
Matt, I always am long-winded. I talk for way too much in the beginning of these. The students and the teachers are already tired of hearing me talk. I know it. I'm going to fully pass it over to you. And if any questions come up, I'm just going to pop on and ask them live. Is that okay?
That'd be perfect. I'd love to hear the questions and yeah, just shout them out.
Great. Please post them in the chat. I'll see you in a bit, Matt.
Thanks, Will. So we're here today to talk about satellites. And we're calling them velocity victors because they're so super fast. We'll talk about that here in just a second. In fact, we're going to talk about the science behind satellites. More importantly, we're going to give you a tour of one of the satellite manufacturing facilities here in New Mexico. And we'll talk a little bit about the space business also here in our great state of New Mexico. In order to do that, I'm going to go ahead and share my screen and just show you a couple of slides, and we'll talk through the science behind satellites. The first thing I want to tell you is a little bit about myself. My name's Matt, and I work for the Air Force Research Laboratory. And our laboratory actually develops the technology for the United States Air Force, and for now, for the Space Force as well. Many of you might have heard of the Space Force, and I joke it's not just a Netflix show, it's actually the sixth branch of our military. So our laboratory is spread out all across the country, which is why I showed you this great map of the United States. And a lot of our work is done in Dayton, Ohio, which is the birthplace of aviation, they like to say. But here at Kirtland Air Force Base near Albuquerque, New Mexico, it's actually our second largest location. And we've got about 2,000 people working on technology in directed energy, which is mostly things like lasers, and then space technology. We're actually the headquarters for all the space technology for the Space Force is right here at our laboratory here in Albuquerque. So I want to talk a little bit, again, about the science behind satellites and why do we call them velocity victors, right? What is that all about? Well, one of my favorite things to talk about with students, and I love to do this in a classroom when I'm actually able to meet with you in person, is why do satellites even stay in orbit, right? I mean, you guys have seen rockets launch before, right? And it's amazing to see this huge rocket goes up, but when I throw things up, they come back down. And if I throw them up really, really high, they still come back down. So what's going on here? And the answer, you can see it on the chart, the answer is actually velocity, it's speed. So a long time ago, Sir Isaac Newton out of Britain, he came up with this idea of if you got going fast enough, you could keep going around and around the Earth and never fall down. And so he did a thought experiment. It's on the kind of the figure here on the lower left, where he showed that if you took a cannon and you shot it sideways and you shot the cannonball fast enough, it actually would never come down. It would keep falling, but because the Earth is a ball, it would never actually hit the ground. So what I'm going to do is show you a simulation of how that works. So they call it Newton's cannon for Sir Isaac Newton. And this is actually a figure of the original drawing that he did in the 1600s. And so if you can imagine on top of that cannon, on top of the mountain, a cannon pointed sideways, you can actually, with this little slider, the link I'll make sure is posted in the chat, you can actually shoot the cannonball at different speeds. So if you shoot it at 3,000 meters per second, it's kind of fast, and you fire it. Whoop. Hopefully you saw it didn't go very far. It actually didn't go into orbit. It kind of crunched off the mountain. So if you speed it up a little bit, that's not fast enough either. But look what happens if you keep getting it faster and faster. Now, Newton didn't have a computer simulation like this. He didn't have a game like I do. He just did it as a thought experiment. But watch what happens if you finally get it fast enough, really, really hard. Hopefully you can see what's happening to my little satellite. Now, this particular satellite's actually going to hit the top of the mountain. Ow! Ow! Because we didn't duck, right? And it went sideways, not up and sideways. But that's actually what's happening, right? The cannonball goes so quickly that it's always falling, but it's falling around the sphere. It can never seem to find a place to hit. And that's actually how satellites stay in orbit. And that's why we call them velocity victors. So how fast is that? Let's talk about that for just a couple of minutes. On the bottom, I've got a little bit of a table there. And for different altitudes of orbits, how high you are going around the Earth, there's actually different velocities that you need so you can continually go around and not crash into the Earth. And those velocities are listed as 8 kilometers a second, 4 kilometers a second, and 3 kilometers a second. And that's just kind of how the math works out. But I don't have any feel for what a kilometer a second is. I don't know about you guys. And so I had to ask myself, how fast is 8 kilometers a second? Is that faster than a car? Is it slower than a car, faster than an airplane? Well, we'll need to do some math to get to something that I understand, which is miles per hour. I've got a good sense of miles per hour. So I'm just showing you what the conversion process is to get from kilometers per second to miles per hour. We know that there are, first we've got to get to hours from seconds. And so we know that there are 60 seconds in every minute and 60 minutes in every hour. So if we just multiply this through 8 times 60 by 60, will actually get us 28,000 kilometers every hour. But I still don't do kilometers an hour. I like miles an hour. So we've got to get rid of the kilometers. We'll go ahead and convert one more time. We know that there's 0.62 miles in every kilometer. And so if we multiply that through, all the units cancel out correctly, and we get down to 17,856 miles an hour. Well, that sounds pretty fast to keep that object in orbit, to keep that satellite going around and around. And it is tremendously fast. If you compare that to something like an airplane, which is like 500 miles an hour, or even a rifle bullet, right? A rifle bullet's got to be faster than a satellite. It's not even close. A rifle bullet's about 2,000 miles an hour. And again, the satellites have to be 17,000 miles an hour to stay in orbit. I didn't know if I said this or not, but my science degree is in physics. So I really like problems like this because it's the physics, the science of physical things and processes that really fascinate me. And that's so fast.
Matt, so, I'm going to ask a quick question that we had come inside the chat, if that's okay.
That'd be perfect, Will.
So we have a question. Joel from Cesar Chavez Elementary in Santa Fe is asking, so how do you make the satellites fly?
So what we've got to do is we've got to somehow get them up above the atmosphere so that they burn up. And then all we have to do is speed them up. As long as we get them to 17,000 miles an hour, they're actually not flying. They're still falling, but they're falling around the Earth, right? They're falling, but they can never seem to hit the Earth because the Earth is a sphere, if that kind of makes sense. So of course, we get the satellites up in orbit with rockets, and you guys have seen lots of rocket launches, I hope. They're fascinating to watch in person. That's not a very common thing to see, but they're even cool on TV. And you basically have to accelerate the satellite. The rocket accelerates the satellite just like your car accelerates from a stoplight, only it's a whole lot more push. And so this is some of the math that's involved in showing how much. But basically, the rocket is filled with kerosene. It's a fuel, almost like gasoline, and they just light it. Very carefully, they keep pushing out kerosene and exhaust out one end, makes the rocket go the other direction. That was another great Newton discovery. We have a lot of things to thank Newton for apparently today. And if you do that for hundreds and hundreds of seconds, it'll eventually get going so fast that that satellite will stay in orbit pretty much forever unless something changes. I want to talk about just a couple more things before we take a tour of our satellite manufacturing facility. The other thing that's really interesting is there are some special orbits. And so for those of you, have you ever used DirecTV or heard of a weather satellite? Those kinds of satellites use special orbits that are up very, very high. And those orbits, those satellites continuously go around the Earth just like all orbiting satellites. But they're up so high that they actually match the rate which they go around the Earth with the rotation of the Earth. And so it appears that they're stationary over one place over the Earth. They're called geostationary orbits. And what I find fascinating about that is above us right now in New Mexico, there are a number of satellites that are actually right above New Mexico, and they're there all the time, and they just rotate around with us. And so one of the weather satellites that NOAA put up, GOES 14, is actually above New Mexico. It's always above New Mexico, and it's actually positioned right above Santa Rosa, which I think is sort of fun. And it can see much of the Earth, and it provides that weather coverage. So go ahead,
Matt,
Will.
We got another question coming. So Robert wants to know, have you ever seen a rocket launch in person?
You know, I have not. Many of the people that I work with have gone to them, but I have never been to one in person. One of the things that made it happen, I didn't get to see it, is because sometimes those rockets wait for really, really good weather. And so I was supposed to go see one and it got weathered out, we call it, and it had to go later and I couldn't see it. But I hear it's amazing to see them in person. So I mentioned that there are different kinds of orbits, and I won't go into too much detail, but you could have a satellite that's very close to the Earth, relatively speaking. It's still hundreds of miles away, but that's pretty close to the Earth in an orbit, and we call that low Earth orbit. Or you could have one in those geosynchronous orbits that I mentioned before, and they're a lot farther away from the Earth. And there's a lot of differences for why you choose one over the other. The biggest difference is that if you're very high up, the Earth looks very small and you can actually see much of the Earth all at once. But if you're down low, you can only see a very small fraction of the Earth at once. I don't know if you guys have seen pictures of the International Space Station and how the satellites, I'm sorry, the scientists and astronaut on the space station can look down at the Earth. They're very low Earth orbit, and so they only see a portion of the Earth at a time, as opposed to if you were very high up. And this is the chart I've been trying to get to here. Those different orbits actually imply different types of satellites. So not all satellites are the same. We say satellites, but they're very drastically different. So on the left is a picture of a satellite that's made by the Boeing Corporation, and it's huge. If you look closely, you'll see those are people in protective gear, clean gear we call it, for a clean room, that are standing next to that satellite. It's more than 20 feet tall, the satellite. And that's one of the satellites that you would put up way high. And it can see most of the Earth at once, almost half of the Earth at a time, and it can broadcast signals down.
We two more quick things. So shout out to Samantha's watching from Cesar Chavez in Santa Fe as well. And then we got another question asking about, and this is a good question. How does the satellite orient itself to face certain things? So if it's in orbit, how is it orienting itself to face the Earth in orbit?
That's an awesome question. So you're right, the satellite needs to do that because it needs to point the antennas and the cameras back towards the Earth. So there's a bunch of different ways it does that. It has sensors on board so it can tell where its position is. One of those sensors they use is called a star tracker. It actually has a camera that measures where the stars are, and so it knows with respect to the stars where the Earth is. And then they use a bunch of different thrusters and things called reaction wheels to go ahead and position the satellite so it's always pointed correctly at the Earth. That's a big part of a satellite. That's a great question. Will, you said you had another one?
Oh, that was it. Just
okay, okay. So I wanted to point out in the upper right-hand corner, the picture with the two folks, they're actually working on a satellite as well. That satellite is called a CubeSat, and it's tiny. It's the thing that they're holding. That is also a satellite that the Air Force has launched, and it does similar functions. That satellite's launched into low Earth orbit, much closer to the Earth, and it can only talk to or see a very small fraction of the Earth at any moment. So those great questions we're having already. And so, what's on a satellite? Well, a satellite actually just has a bunch of the same stuff that's on a cell phone. Actually, that was my cell phone I took a picture of. So satellites have kind of the same thing as cell phones. They've got antennas on them. They look a little bit different. The antenna on your cell phone is flat and it's inside the phone. So, sometimes the antennas look like these dishes that you see in the model that's on the both picture and I'm holding here. It's got cameras on it, global positioning systems, batteries. Both your cell phone and the satellite need electricity, and they get it from different ways, right? Most cell phones you plug into the wall to charge them. Or you could use solar charging for them, I guess. And pretty much all satellites use solar panels, right, to charge up their batteries. Both satellites and cell phones have computers and different kinds of sensors. There was a great question about orientation of a satellite. You know that your phone also has sensors, and it can tell what orientation you have it as well, which is pretty cool. So really, if you launched your phone into space at 17,000 miles an hour so it would stay up there, it actually would make a pretty decent satellite.
We have a question coming in from Cesar Chavez Elementary, again here in Santa Fe, from Noah Mays. Noah's asking, how is the rocket project going to fly?
The rocket project, I'm not totally sure what that is. So lots of We do a lot of research on rockets, but there are lots of companies like SpaceX and Boeing and Lockheed Martin that make rockets already. In fact, I don't know if you saw SpaceX launched a rocket a few days ago with 4 astronauts on it that went up to the space station.
Yeah, and I think they just docked yesterday as well, right?
That's right. They actually got to the space station. So by the way, those astronauts are now moving at 17,000 plus miles an hour.
Wow.
Again, they're always falling. That's why they're weightless, because they're falling forever while they're up there. It's just that they're going forward so quickly that they can't possibly find the Earth to hit, which is awesome.
Yeah, amazing. And I want to give a shout out to Miss Webb's class as well, who's watching on the stream. I'll kick it back to you, Matt.
So I want to give you guys a tour of one of the laboratories that's in Albuquerque at Kirtland Air Force Base that AFRL uses to develop satellites. And in particular, we don't usually in Albuquerque work on those really, really big satellites we showed you. We're doing a lot of research on these small kinds of satellites. So, Will, I hope everyone can still see me. I can't see everyone else. But we do satellites that are much smaller, like in this picture, and they call them CubeSats. Well, and the reason they call them CubeSats is because they're often shaped just like this. This is a model of a satellite, but it's a CubeSat for, can you guys guess why they call it a CubeSat? Hopefully you can see it okay. It's in the shape of a cube. And that shape isn't necessarily important for the satellite. It could be anything in space, but it's actually important for getting it launched. And I'll talk more about that. And so this CubeSat is 10 centimeters by 10 centimeters by 10 centimeters. Right, and that's the kind of satellites we work on. Amazing to think that they actually work in space. This is actually a real satellite. This is a CubeSat that's not a cube anymore because we put 3 of them together. So it's 3 CubeSats hooked together. And we didn't finish this. We just use it as a demo now. But it has antennas on it, and this is where the solar panels would go, and the electronics would be inside this hole. We didn't put those in either. We saved some money on this demonstration. So these are the kind of satellites I want to take you and show you the laboratory where we make them next. So I'm going to jump over to a video, I hope. And so this is what we call our small satellite integration facility. Again, it's near the airport here in Albuquerque. You can tell it's a very, very large facility. It's typically a very clean facility. And these are a bunch of the students that were working here a couple summers ago doing some summer projects. So let me show you the satellite. Satellites need to be kept clean. And so you can see these 2 folks are working on this. This is actually a 6 CubeSat, we call it, because it's 6 times longer than the one I was showing you. And they're working on putting some of the internal electronics in it, the processors, the radios and things like that into the CubeSat. These things typically cost hundreds of thousands of dollars, frankly. Not because the parts are that expensive, but because of all the time we put in on them. They're continuing to put pieces on, and I'll show you the finished one here in a second and how we test it. So this is a view where most of the parts are on now. These gray objects are called patch antennas. They're antennas. They're not like a dish. These actually radiate in all directions. And that actually gets to the question that was asked earlier. They radiate in all directions in case the satellite's pointed the wrong way. We still have a hope of being able to talk to it. And now this is the almost finished satellite, and you can see that the outside is almost entirely covered with different kinds of solar cells. We're trying to collect as much light as we can to charge the batteries. This is a satellite that's in low Earth orbit, and so as it goes around and around the Earth every 90 minutes, half of that time is in the daytime or when the sun is shining on the satellite, and the other half is at nighttime. And so we have to get enough power into it in that 45 minutes when it's in the sunshine for it to last on the dark side. So we put as many solar cells on as we possibly can. And then a lot of work on satellites and a lot of the cost goes into testing. You probably realize that we don't fix these satellites once they get on orbit, right? So they have to work really well once they get there. It would cost so much to bring them back and slow them back down, or to send like a repair person up, right? That we don't often do that. It's very rare. And so we test them a lot to make sure they're going to work. The other interesting thing, and one of the reasons we use these CubeSats, is that we talked about launching satellites on a rocket. And typically, oftentimes, we put big satellites on their very own rocket. We buy one big satellite and we buy one big rocket. But it wouldn't make any sense to put this little satellite on a big rocket, and we don't have very many little rockets. So what they're doing is they're actually going to package this satellite in a different kind of box and send it up as cargo. I'll show you what that looks like. So they're actually stuffing this satellite, it's the completed product now, into this box. And the box is kind of like a Pez candy dispenser. I don't know if you're familiar with those Pez dispensers. You kind of open the top and the candy shoots out. Very, very similar. There's a spring at the bottom of the box. And when this gets in orbit, they open the door and the spring pushes the satellite out into space. I'll show you that here in just a second.
We have a couple of questions coming in on that. First up, this is a good question that Logan wants to know. So Logan's asking if there's more than 3 satellites, you're talking about this, this long satellite that you're discussing here, will the weight be distributed differently in space than when it's launched?
Yeah, I mean, if I get the question correctly, you can put one long satellite in or 3 smaller ones, and yes, all of these things like where the weight is within the satellite, where it is on the rocket, all of the things matter an awful lot. Once you get up to speed in orbit, right, you're no longer, you don't have any weight, right, because you're always falling. But certain properties beyond weight, like center of mass and other things, are still very important for satellites.
Great. Okay. And so that smaller cube satellite that you had there on the screen, so is that the smallest a satellite can be?
No. And in fact, we have launched ones that are 1/6 of that size, about this size. And in theory, you're right, your cell phone would make a pretty decent satellite if you put solar panels on it. And so a satellite can be almost any size as long as you can do the functions required, right, to get power into it, to get communications into it, and things like that. They're getting smaller all the time.
Angelica at Cesar Chavez wants to know, will the satellite ever land or crash?
So as I mentioned, if you get it going fast enough, it'll just keep going around and around and around the Earth. Except for one problem. At low Earth orbit, space isn't really a vacuum, right? Even up that high, there's enough air particles that actually the satellite's going so quickly, it starts to hit what we call drag. It starts to slow down. And so a lot of satellites that are in low Earth orbit actually start slowing down from those few particles of air that are up there. And what happens is they'll start going slower and slower. And just like that simulation I showed you, eventually they'll go so slow that they won't quite make it around the Earth. And they end up hitting the atmosphere and what we call either burning up, right? They get so hot from all that air and that friction, or they actually just make it all the way down and maybe hopefully land in the ocean. And so a lot of times satellites burn up. It's what we call it burning up in orbit. All right, a couple more things on this 6U CubeSat. I mentioned testing. So now these guys are actually putting that packaged satellite, it's in its box now, onto what we call a shake table. So if you ever go visit a launch, and I haven't seen one in person, you hear a lot of low rumble that creates a lot of vibrations. And so this table actually shakes the satellite in its container to make sure it won't break, or at least if it breaks in our laboratory and not on the rocket. They've got it all strapped down before they shake it. Sometimes we operate them when they're being shaken, and sometimes we just test them before and after the shaking to make sure they still work. So now what's happened is you see 4 of those long boxes. So our satellite was put with 3 others to make now a 4-pack of boxed satellites. And that's important because what they're going to do is put all 4 of those satellites in, apparently we like boxes a lot, in yet another box. And this was shipped to the launch site, where it actually went on the cargo container, the cargo launch up to the International Space Station. So when they were putting in whatever they sent to the astronauts, right, new supplies, lettuce, Legos, whatever goes up there, they put this scientific equipment, important things, I'm sure, they put this up as well. And that went up in the same rocket. And then what the astronauts did in this case is they actually took the satellites out of the big box you saw there, and they put all those 4 containers onto the arm of the International Space Station. That's what this is. It's the end of the arm. And you can see that this is a picture of one of those containers being opened up, and our satellite is being pushed out by the spring. This is only a photograph, but if it was a video, you'd see it being pushed relatively slowly out into space. Since the space station's going at 17,000 miles an hour, then our satellites are going 17,000 miles an hour as well, and it'll stay in orbit for many, many months. And the last shot I'll show you is a very distant shot of a couple satellites, I hope. Yeah, there's two of them now at a fair distance, actually flying away from the space station. So again, all of these went up in a rocket, but these little satellites didn't get their own rocket. They went up with cargo to the space station and then got kicked out after the fact. All right, Will, is there any other questions? I only have about one or two more topics.
Yep, we got a couple of questions that came in. Lorenzo would like to know, how long does it take to make the satellite?
That's a great question, Lorenzo. Typically about 2 or 3 years. And the reason, when we make them, so when AFRL makes them, they're almost always, we're testing something new and something different, maybe a better radio, maybe a smaller satellite. And so what takes all of that time is all the design work. There's a lot of computer modeling as well on different types of computers to make sure we understand how it's supposed to work. And so if you look at all of that, it takes several years.
Okay. And this is a good question too, coming from Roran. I think I'm saying that name right. So if we have too many satellites in one place or over the Earth, will it become a problem down the line?
Yeah, in fact, it's a great question, and it is becoming a bigger problem. I mentioned that a lot of these satellites don't ever fall out of the sky, right? They're up high enough so they don't ever hit enough drag to come back. And so, right, you're putting up satellites all the time, they're not coming back, right? So satellite collisions are actually a problem. They're a thing that happens. We in the Air Force and Space Force, we track all of the objects in space, right? And we try to keep track of them where they are and make sure we tell people if they're going to collide, but it is becoming an increasing issue.
We got 2 questions in from Justin. So Justin wants to know if the International Space Station is in low orbit, does it have to accelerate every once in a while?
Yes, it does. So wonderful question and very insightful. Yeah, so they have thrusters on the space station, and they have to push it up, increase its velocity quite often because all of the drag on the space station. If they didn't do that, over a period of time, it would eventually burn up in the atmosphere. And so they take up propellant on these resupply missions, and they fire the thrusters to keep it going fast enough to stay up.
Wow, okay. And the second question from Justin is asking how many satellites you can launch at one time.
So you could imagine you could put a lot of these on the same kind of rocket. I'm holding up this 3U CubeSat, we call it, on the same kind of rocket that big one from Boeing flies on. But that gets to be a little bit painful. Typically, the biggest number I've seen is about 100. But let me actually show you my next slide, if I can, a company that's launching 60 on every launch routinely, if that makes sense. So what I wanted to talk just briefly about is all of the new companies and the new work happening across the world and across the US and in New Mexico in what we call new space or space 2.0. And a lot of this is happening here in Albuquerque and across the state of New Mexico. Because the technology is getting better, things are getting smaller, as you guys recognize. It's just been a lot easier to run a business in satellites. And so as an example of that, many of you might have heard of SpaceX. They're the company that helped launch, that actually launched the astronauts the last couple of days. But they've been launching satellites by the hundreds. So that picture next to their SpaceX building is actually what they call flat pack satellites. They actually pack these 260 kilogram satellites, that's about 400 pounds, into the rocket. And they're kind of smashed satellites. They're not cubes. They're actually in a funny shape just so they can pack them in, because they launch them 60 at a time. Their goal is to provide internet from space, and you can actually go online and find out more about how they're doing. They're starting to actually sell that for about $100 a month, I think. Similarly, Planet Labs is actually doing something with very small satellites. Their satellites are not much bigger than this one here, and they're putting cameras on them. And they're putting lots and lots of satellites up there so that they get pictures of things that no one ever thought we'd catch pictures of. So this little picture up in the corner is just an example of they caught a particular volcano erupting. They didn't plan to catch that, but they happened to be looking down at the right time and got that picture. The other thing that's happening is people are using all of this great data from satellites in brand new ways. And our own Descartes Labs, it's a company up in Santa Fe, a growing company, is doing amazing things in predicting like how much corn is going to be grown around the world or other things by basically looking down at the Earth from satellites, taking all those pictures and using advanced algorithms and artificial intelligence and machine learning to figure out important things that people need to know. Like, is there going to be enough corn for everyone? Or is there more drought in areas than we expected? And they're doing all of that from space. And the last slide I wanted to show you is, again, many of the things that are going on in what we call new space or space 2.0 are happening right here in New Mexico. And so there's a new organization called New Space New Mexico that's helping drive a lot of innovation and work with all these companies. I mentioned the Space Force earlier. You might not realize that there's a number of organizations on Kirtland Air Force Base and around the state that are now part of this new Space Force. It's not something to talk about for the future. It's here now. I know lots and lots of folks now that are working for the U.S. Space Force right here in Albuquerque. And then finally, I'll mention Virgin Galactic. You folks might have heard that in our own Spaceport America down by TRC in the southern part of the state, we're expecting to have some of the first tourism launches, essentially, of different folks looking for a ride to space here in the next year or so. They call those suborbital flights because those flights will go up for 4 or 5 minutes, and then they'll kind of turn over, they call it a little bit, and they'll be weightless for a few minutes, and then come back and land here in New Mexico where they took off from. Again, they're not going nearly fast enough to stay in orbit, but it's just an amazing ride for a few minutes. For those tourists. They're also doing some experiments that go with that. The last slide I want to talk about, but I'll ask for questions, Will, first.
Okay, great. We did have some questions come in. So Lorenzo would like to know how much money it costs to make a satellite.
So it's all almost completely dependent on how much time you work on it. For the ones that I mentioned before, if we make a satellite at the Air Force Research Lab and we spend a couple of years on it, it usually costs, say, $5 million on that order. The satellites that SpaceX is making, they're making many of them and they're all the same. I think they're probably only a few $100,000. It's still kind of a lot. That big one I showed you, if you remember that big Boeing satellite, we've bought quite a few of those in the Air Force and they cost about $350 million. Wow. And it's just because those take so long to make and so many people have to work on those giant ones that they cost that much money.
And a question that came in is asking about the technicians you were showing in your previous videos. They're wearing a lot of personal protective equipment. So why do they have to wear things like hairnets and sort of stuff like that?
Most of that isn't to protect those workers. It's actually to keep the satellites from getting dirty. The satellites have sensitive electronic equipment on them. And also when you go up into space, if there's any dirt or oils from like your hands on the satellite, it actually evaporates or sublimates or it does something funky in the vacuum of space. And that's not something we want to see happen. And so they're mostly just trying to keep everything clean.
Presley would like to know how many satellites there currently are in space.
That's an awesome question. So I think we currently track about 26,000 different objects in space. And remember, those satellites are all the things that people meant to put there, like things like this, right? But it's also a bunch of other junk, like parts of satellites that might have broken up, pieces of rocket that are still up there. So I think there's about 26,000 active pieces of stuff, and maybe only about 1,000 or 2,000 of those are really satellites that you could talk to.
Awesome. Let's see. So Logan's asking, is it possible in a few years that some of our satellites could be in orbit around other planets in our solar system?
Well, in fact, yes, and that's happening now. So when we have sent people to the moon, right? The typically back in the 60s, that was a two-part affair, right? There was a lunar lander, but there was a command module that stayed orbiting the moon in that particular case before it came home. And even today, you know that there's a number of different Mars rovers. And I'm pretty sure those Mars rovers went to the surface of the planet Mars, but there's actually orbiting vehicles still going around Mars, taking data, taking pictures of Mars, doing all sorts of things. And so absolutely, the physics is the same for every planet. And it'll be neat to see us put more stuff around other planets.
Mm-hmm. So is it possible then to make these satellites smaller than our own hands? I guess, but as you mentioned earlier, you can make a satellite as small as a cell phone, right?
Yep.
Yeah. So it's absolutely possible, Logan. Good question. So for all these thousands of satellites that you're mentioning here, is there someone who monitors these satellites, or is it like artificial intelligence, or what does that look like for those satellites?
So the satellites typically monitor themselves, but in addition, the Space Force currently is actually measuring where all the satellites are. All those 26,000 objects I said, we actually have a huge database of what their orbits are. We have radar systems and cameras that remeasure and check their position. And then we've got lots of complicated software and AI that actually predict where those satellites are going to go, whether they're going to hit each other, those sorts of things. So it's a pretty big job. Think of it kind of like air traffic control, but for satellites.
Wow. Okay. Awesome. Do we have any more questions, students? It looks like that might be all the questions that we have coming in the chat for right now.
So the last thing I wanted to talk just a little bit about is opportunities to get involved, right? In sort of aerospace and these kind of careers. There are lots and lots of different ways, different pathways, if you would, to get into these sort of things. Whether you're interested in being a technician, interested in collecting data, maybe being a scientist to develop the next sorts of algorithms that'll run on computers on satellites. There's all sorts of ways to get involved. And again, New Mexico is a great state for this. We've got universities and community colleges that participate in this kind of work. And there's a lot of opportunity for students to even get involved. One of the ones I know about and I listed on this screen is what we call internships. And those are opportunities for, in our case, paid work, working on things like CubeSats and like software that helps control satellites. Other organizations like Sandia, companies, often they all have these kinds of internships, and the universities do as well. So I guess I would encourage you to think about this as you go through your own education. And if you're excited about science or engineering or math or any of the STEAM aspects, look for opportunities to get involved, because we're looking for you. We need your ideas and your brilliance, to help keep all this stuff amazing into the future.
Awesome.
And that's what I had to talk about today.
Great, and please take advantage of that, students. If you want that link, we can share that as well inside the chat. So we'll post that on our YouTube chat. So please take advantage of that. AFRL, Air Force Research Laboratories, really is an amazing resource that we have here in the state of New Mexico. We have some questions that are still flowing in the chat. Is scrolling faster than I'm having time to sort through it here. But so Lorenzo is wondering how big a satellite can be.
So that's a great question. The current limit is basically, so when it goes up on the rocket, it has to fit inside the rocket, right? So the current limit is the biggest rocket, they call it a fairing. That's the part that goes around the satellite as it launches, is 5 meters in diameter. So what's that? A little over 15 feet. So it can be about 30 feet tall and 15 feet in diameter. Otherwise, there's not a rocket big enough to get the thing into space. But that's a pretty big satellite. They're about 10,000 pounds when they're that big. That's a big satellite.
Wow, 10,000 pounds. That's honestly, it's hard to wrap my mind around that number. That's amazing. So this is a great question from Miss Williams' class. So they're asking, what kind of education do you need to have in order to work on satellites?
So that is a great question. So there's a lot of different educational pathways. So we have a lot of our workforce have advanced degrees in like science and engineering. We also have a lot of our team members have bachelor's degrees. We have technicians and folks that run the equipment. They might have a 2-year degree, like from a community college. So there's a whole bunch of different ways to get involved. The other thing, and I know this is a STEAM discussion, is half of our workforce at AFRL are scientists and engineers, and the other half do all those other things, right, that keep our big operation running. So we have security people and contracts people and finance people, educators, all sorts of things. So, and those folks love rockets and satellites as well. And so there's a whole bunch of different pathways to get involved in this kind of career.
it takes a city, doesn't it?
Yeah, that's right.
In some certain ways. Cheyenne is wondering, how do we communicate? I guess the question would be, how do you communicate with satellites to take pictures and then also to receive those pictures that the satellites take?
Yeah, it's almost always right now with radio links. And so many of the satellites will have what they call satellite dishes on them, right? Which basically are aimed back to a similar radio antenna on the ground. And we use frequencies that are not a whole lot different than your FM stations, right? And we basically talk back and forth with those things. We send commands up and tell the satellites what to do. And then we receive a high data rate data down when they get that picture.
So then is there a bit of a delay between those if it is radio waves?
Yeah, there's a significant delay. I mean, it's not a lot to us, but for those of you that are into computer gaming, one of the reasons that people want to put internet satellites low Earth orbit, not far out, is because of that delay. The delay to get to geo and back, geosynchronous orbit and back, is long enough that it actually makes computer games not work very well.
And this would hold true for things like the Hubble Space Telescope or anything like that that's way far out there in space and getting those pictures back to us, right? This question is coming from Roran Hensley asking, is running out of different frequencies a problem?
It's a huge problem. Great question. In order to be able, yes, so there's not too much radio interference. I'm trying to hard to explain this. You have to ask to use a particular frequency in a particular location. And yes, we are completely running out of those frequencies. One of the research areas that AFRL is working on is looking at some unused frequencies that people haven't used because those radio waves don't go through clouds very well, for example, and trying to understand, even though they're less preferred, can we use those anyway? Because the popular frequencies are all taken up with other satellites already.
That's amazing. That's amazing. Okay, it looks like those are all the questions that we're getting in. But don't forget, we did share that link to AFRL's program there inside the YouTube chat. So please check it out, and reach out to somebody at AFRL as well. They're fantastic people. I can firsthand attest to this. So please reach out. I know they would love to connect with you if you have any questions or any follow-up. Otherwise, Matt, thank you so much for being on today.
Thanks, Will. It was a ton of fun.
All right. Well, see you later. Take care. Thank you.
Bye-bye.
And students and teachers, I want to give a final shout out to some of our sponsors. Again, without these folks, none of what you're seeing would be possible. So thank you so much to our sponsors for this event: Honeywell, Fidelity Investments, Aztec Machine and Repair, Air Force Research Laboratories, DITRA, Kirtland Air Force Base, Micronet Solutions, Presbyterian Hospitals, and Sandia National Laboratories. Thank you all so much. Please come back, join us tomorrow. So tomorrow morning, beginning here at 9:30, we have Central New Mexico's coming back on. We also have Arizona State University. So if any of you high school students are thinking about going to ASU, join us tomorrow. That should be a really great presentation. And don't forget, you can check out the rest of our live stream schedule at our website, discoveryfestnm.org. We're going to drop that in the chat. So please take a look at the schedule of events there. We'd love to have you back for that. Otherwise, please stay healthy, stay safe, everyone, and we will see you soon. Take care.